Hello kids, I'm Chavi Bansal and hope you have seen my previous video. So in the previous video, we have talked about the equilibrium. What is equilibrium and what is forward reaction, what is reverse reaction, and how to calculate the equilibrium constant. So in today's video, we are going to talk ahead of it. We are going to talk about the different types of equilibrium constants. What are their relationships and what are the factors that are going to affect the equilibrium constant? And what all components should be present and should be considered while calculating the equilibrium constant. Fine. So let me share my screen. Just a second. Yeah, I hope you guys are able to see my screen. Fine. So if you remember, we started with calculation of K equilibrium. For example, let's take an example of a reaction. Right? So how we are going to calculate K equilibrium? K equilibrium is equal to the concentration of the product raised to power their stoichiometric coefficients divided by, and plus the states are also very important. We'll talk about how the states are going to play a role in calculating the equilibrium constant. For now, let's assume all the compounds that are present here, they are all present in the gaseous state. Fine. So what is the equilibrium constant? It is the concentration of the product raised by their stoichiometric coefficient divided by the concentration of reactants raised by their stoichiometric coefficient. Right? Now, other than this, there is another term called as Q also, Q equilibrium. Actually, it is not called as Q equilibrium, it is called as reaction quotient. Now, what is reaction quotient? For example, K equilibrium is calculated using the concentration of reactant and product at equilibrium, right? Now, what if we have to calculate a constant or a number before and after equilibrium? So this reaction quotient is the ratio of concentration of products raised to power their stoichiometric coefficients stoichiometric coefficients divided by the concentration of reactants raised to power their stoichiometric coefficient. Okay, now you will ask me what is the difference. So the difference here is K equilibrium is calculated only at equilibrium, whereas reaction quotient can be calculated at any point. Okay, so for example, just at the start of the reaction, maybe at time equals to 2 seconds, maybe time at 10 seconds, anywhere, at any point, we can find out the reaction quotient. And at equilibrium, Q becomes equal to K equilibrium. Okay. So that's why when when the reaction reaches to the equilibrium, the reaction quotient at that point is called as K equilibrium. Clear? Now, why I have introduced about this, we will talk about that later. But before, we are going to talk about the different types of equilibrium constant. Equilibrium constants. So what do I mean by different types of equilibrium constant? So they are generally of three types. One is called as Kc, where the constant is with respect to concentration of the components. Next is Kp, where we are going to find out the partial pressure of the components, and then accordingly we are going to find out the equilibrium constant. So Kp, when partial pressure of the components are considered. Okay. And the third is K psi, where we are going to use the mole fraction as the active mass of the reaction. Okay. Now, let's see individually how we are going to calculate them and what does a concentration, a partial pressure, or a mole fraction means here. Okay, so let's take another again the same example. A plus B is forming C plus D, and all the components are in the gaseous phase. Okay, now in such cases, what is concentration now? Concentration is nothing but molarity. Okay, and molarity is given by number of moles divided by volume. Okay, so concentration is what? Molarity, and concentration can be calculated using the given formula. Okay, now let's make an ICE table for the reaction and understand how we can express K equilibrium in terms of Kc. So let's assume initially there was 1 mole of A and 1 mole of B present, right? And no moles of C and D. Fine. What will be the change till it reaches to the equilibrium? X. It will be AX, BX plus CX plus DX, right? So what is the concentrations at equilibrium? 1 minus AX, 1 minus BX, CX and DX, right? So these are the number of moles. Let's divide it by volume. So this gives us the concentration of each component at the equilibrium. And now the K equilibrium will be called as Kc, which will be the concentration of C raised to power C, concentration of D raised to power D, concentration of A raised to power A, and concentration of B raised to power B. Okay. In this way, we can substitute these value, which is Cx upon V raised to power C, dx upon V raised to power D, 1 minus ax upon v raised to power a, and 1 minus bx upon v raised to power b, right? So the equilibrium constant here will be given by Kc. This is the equilibrium constant where we express the components in terms of concentration. Clear? Next is Kp. Kp, it considers partial pressure. Now, what is partial pressure? So for example, assume, so there are like 10 students in the class and each of the student has got their physics marks, okay? And the sum total of the class is 800, right? Now, out of these 10 students, student A got 35 marks in physics. So what is the contribution of student A to the total marks is 35 by 800, right? Same goes with the partial pressure. So what is partial pressure? Pressure exerted by a gas in a mixture of gases. Okay, so what is the pressure exerted by gas in a mixture of gases is called as partial pressure of that individual gas. So by seeing the definition of partial pressure, I think we all can say that Kp can be only expressed if at least one component of the reaction should be in the gaseous phase, right? If none of the components is in gaseous phase, we will not be able to find out the value of Kp. Clear? Now, let's find out the value of Kp, that is using the same equation. Okay, AA plus BB forms CC plus DD. Okay, now instead of using the number of moles, let's assume that this is the partial pressure of A, partial pressure of B, partial pressure of C, partial pressure of D at equilibrium. So K equilibrium will be equal to Kp, which will be equal to partial pressure of C raised to power C into partial pressure of D raised to power D, partial pressure of A raised to power A, and partial pressure of B raised to power B. So this is called as Kp, or equilibrium constant expressed in terms of partial pressure. Clear? Next is K psi. K psi is what? This is mole fraction. Now, what is mole fraction? Nothing. Mole of a component divided by total number of moles. So, for example, again, the same reaction. Okay, so the number of moles at equilibrium is, let's assume A, B, C, and D. So the total number of moles at equilibrium will be equal to A plus B plus C plus D. So mole fraction of A will be A divided by A plus B plus C plus D. Same way, mole fraction of B will be B divided by A plus B plus C plus D, where this A, B, C, D are the number of moles of individual components present at equilibrium. Okay, same way C and then D. So A plus B plus C plus D, right? And at that point, if we are going to express K equilibrium, which will be equal to K psi, it will be equal to the mole fraction of D raised to power D, mole fraction of C raised to power C, mole fraction of A raised to power A, and mole fraction of B raised to power B. Clear? Any doubt? Fine. So these are the three types of equilibrium constants that we. Okay. So this was case I, and now we are going to talk about how we can find a relationship between Kc, Kp, and K psi. Okay. So let's start with the same equation. Let's take the same equation. One second. So AA plus BB forms CC plus DD, gaseous. Okay. Now, if I'm going to find the Kp value will be equal to partial pressure of C raised to power C, partial pressure of D raised to power D, partial pressure of A raised to power A, and partial pressure of B raised to power B, right? Now, if you know, we can write PV equals to nRT. So pressure equals to nRT upon V, right? So then I write NC VC RT raised to power C, ND by VD RT raised to power D, NA VA RT raised to power A, and NB VB RT raised to power B, right? If you see, the RT in all the four terminologies that I used here is same, right? I can take it out. So it will be NC by VC raised to power C, ND by VD raised to power D, NA by VA raised to power A, and NB by VB raised to power B, and RT raised to power C plus D minus A plus B, correct? But do you think that this NC upon VC is what? This is concentration. So can I write it as concentration of C raised to power C, concentration of D raised to power D, concentration of A raised to power A, and concentration of B raised to power B, RT raised to power C, once again, RT raised to power C plus D minus A plus B, right? Now, what is this CDAB? This is what? This is Kc. So then I write Kp equals to Kc, RT raised to power C plus D minus A plus B. Now, what is this C plus D minus A plus B? C is the stoichiometric coefficient. C and D is the stoichiometric coefficient of products. And A and B is the stoichiometric coefficient for reactant. So, can I write Kp equals to Kc RT raised to power delta Ng, where delta Ng is what? Change in number of moles of gaseous product minus reactant. So number of moles of gaseous products minus number of moles of gaseous reactants will give you delta Ng. Okay. So Kp equals to Kc RT raised to power delta Ng. So this is the relation between Kp and Kc. Fine. Let's find out the relationship between Kp and K psi. Okay. So one more thing before we go ahead. So partial pressure of any component, like for example A, can be written as mole fraction of A into P total pressure of the mixture, right? So using this, we can, again, what is the Kp value here? Kp value is Pa raised to power A, once again, Kp value is equal to Pc raised to power C, Pd raised to power D, Pa raised to power A, and Pb raised to power B, right? This is the value of Kp. Now, can I write partial pressure of A as mole fraction of A into Pt raised to power C? Sorry, partial pressure of C raised to power C. A mole fraction of D into P total raised to power D. Mole fraction of A into Pt raised to power A, and mole fraction of B into Pt raised to power B. Again, let me take Pt common. So Hc raised to power C, Hd raised to power D, A raised to power A, B raised to power B into P total, C plus D minus A plus B. Now, what is this? This is nothing but K psi, right? So Kp equals to K psi P total raised to power C plus D minus A plus B. So Kp equals to K psi P total raised to power delta Ng. This is the relation between Kp and K psi. Fine. Now, can I write both the equations here? Kp equals to Kc RT raised to power delta Ng. Fine. Now, in which condition do you think Kp, Kc, and Ksi are going to be equal? So, if Kp and Kc are equal, then RT raised to power delta Ng is equal to 1. And if delta Ng is equal to 0, then Kp is equal to Kc equals to K psi. So even if like the number of moles of gases on left side is same as the number of moles of gases on the right side, then the Kp, Kc and K psi value will be same for all of them. Is it clear? Next, we are going to talk about the units. Now, if you have to find out the units of Kp, Kc and K psi, how you can find out the units? It's very easy. You know the formula. Kp equals to Kp is in terms of partial pressure. So pressure is in generally atmosphere. Atmosphere raised to power delta Ng. Why delta Ng? Because everything is expressed in terms of pressure. So atmosphere raised to power delta Ng. Same way, the Kc ka is number of moles upon volume raised to power delta Ng. These are the units of Kp's and Kc. Any doubt? Fine. Now we are done with the different types of equilibrium constants, the relationship between Kp, Kc, and K psi, right? Now let's talk about what and how and what all things has to be considered while calculating the equilibrium constant. Fine. So first, for example, let's take an example. H2 gas plus I2 gas forms 2Hi gas. Okay. For this reaction, we can express Kp and Kc both, right? Why Kp? Because at least like all the components are present in the gaseous phase. So Kc is equal to Hi concentration raised to power 2 upon H2 concentration into I2 concentration, right? Same way, Kp will be equal to the partial pressure of Hi the square upon partial pressure of H2 into partial pressure of I2, right? This will be the value of Kp. Now, this type of reaction, when all the reactants and products are in the same phase, such reactions are called as homogeneous reactions. Okay. Such reactions are called as homogeneous reactions. Now, if one of the reactant or the product or any of the reactant and product, if it's in a solid state or it's in a liquid state, then we do not include them in the calculation of Kc and Kp. Why is it so? So, you know, the solid and liquid concentration does not change much because their their density is so high that very less amount of molecules are used up in changing in the reaction, and their concentration is not highly changed. So we do not consider the solids and liquid concentration when we are calculating the value of Kcs and Kps. Fine. Let's take an example. CH3COOH. This is aqueous, okay, and it is forming CH3COO negative aqueous plus H positive aqueous. Now, all the things are in aqueous position, so Kc will be equal to CH3CO negative into H positive upon CH3COH, right? All are in aqueous state, right? All of them will be included. But now, if, for example, NH3 aqueous And yeah, one more thing. For such reaction, we cannot define Kp, right? Because none of the reactant nor of the product is any of them is gaseous phase. So we cannot consider it for the calculation of Kp. Now, next is, for example, NH3 aqueous plus H2O liquid. Okay. And then it is forming NH4 positive aqueous plus OH negative aqueous. Now, this H2O, the value of this Kc value will be equal to NH4 positive into OH negative divided by NH3. Why I'm not included H2O here? First, everything is in aqueous and H2O is in liquid state. And liquid state here, H2 is used as a solvent, which is present in excess. Means you are taking a whole big jar of water and then you are adding these components into it. So it is doing nothing. It is just acting as a solvent whose concentration is not going to change in the reaction. Okay. So therefore, we do not consider water in this case. Fine. Same way, for example, CaCO3 gas is, CaCO3 solid forms CaO solid plus CO2 gas. Now, this type of reactions are called as heterogeneous reactions, where at least like not all the reactants and products are in the same phase. So some are in solid phase, some is in gaseous phase, right? So the value of Kc will be what? Concentration of CO2. Okay. And even the value of Kp will be the partial pressure of CO2 only. Why? Because other components, other things that are present here, they are in the solid state, and we do not consider the concentration of the solid state while calculating the equilibrium constant. Clear? So this is what we have to do when we are going to calculate the equilibrium constant. So keep this point in mind. Density or concentration of solid or liquid is constant during the chemical reaction and hence is not considered while calculating the equilibrium constant. But if the whole reaction is in liquid state, for example, let me take an example. For example, CH3, COO, C2H5 liquid plus H2O liquid. And then the reaction is CH3COOH liquid plus C2H5OH liquid. In this case, all the components are in the liquid state, right? In that case, we have to consider the concentration of H2O. H2O is not like an excess solvent here. H2O is a part of reaction and its concentration is going to change, and the concentration change is going to matter because all of them are in the liquid state. So CH3COH into C2H5OH divided by CH3COO C2H5 into H2O. So what I can summarize from all these points is, first, whenever there is a homogeneous reaction and all the components of the reactions are in the same phase, those all are considered during the calculation of Kc and Kp. Fine. If none of the reactants or the products are in the gaseous phase, Kp cannot be expressed. Clear? Now, for example, if some of the reactants and products are in aqueous state and some of them are in liquid state, then the liquid state concentration is not to be considered because that is in the excess solvent. But if all the components of the reaction, reactants and products are in the liquid state, then H2O has to be considered. Fine. If in case of heterogeneous reaction, there is a solid, gas, liquid, then only the gaseous component has to be considered while calculating the Kc and Kp, because their density, their concentration changes a lot because they do not have the fixed volume. They have the volume of the container. So their concentration changes during the reaction, whereas the concentration of solid and liquid does not vary that much. That's why we do not consider them while calculating the value of Kc and Kp. Clear? So this is what, and this is how we are going to calculate the Kcs and Kps. Okay. Next is about the phase equilibrium. So what happens when there is a phase equilibrium? When phase equilibrium means, what is phase? So a compound can exist generally in three states: solid, liquid, and gas. And when the solid state and liquid state is in equilibrium with each other, this is called as phase equilibrium. Same way, when liquid and gas are in equilibrium with each other, then it is called as phase equilibrium. Fine. So such cases, what we do is, for example, uh, NH4HS is solid, okay, and it is going to form NH3 gas plus H2S gas. So again, same rules. Kp will be only the pressure of NH3 into pressure of H2S. We do not consider this solid. Okay. Same way, if we have like NH3 aqueous plus H2O liquid, common NH4 positive plus OH negative, aqueous. All are in aqueous state. In that case also, we are going to calculate the value of Kc, and H2O we are not going to consider because H2O is in the liquid state. So what is the value of Kc? NH4 positive concentration, OH negative concentration upon NH theta concentration. Fine. Now, when so this is how you define the Kp's and Kc's when there is a chemical equilibrium as well as there is a phase equilibrium. Fine. Now, next is reaction question. We considered the value of Q, right? We did this. So QC and KC we are going to deal with. So what is QC and what is KC? Again, QC is the reaction question considered in terms of concentration, and KC is the reaction equilibrium constant in terms of concentration, right? Now, I told you Q can be at any time, right? So if QC value is less than KC value, if QC value is less than KC value, means the product has not, the concentration of product is less and the concentration of reactant is more, right? So the product concentration has to increase and the reactant concentration has to decrease. And it takes place only when the reaction moves in a forward direction. So whenever QC is less than KC, then reaction moves in a forward direction. Okay. What do I mean by this? I'll give you an example and I'll explain. Let me explain the other things also. When QC is equal to KC, it is already at equilibrium. There will not be any forward change or a reverse change that will not take, like that will take place and, shift the equilibrium. Now, when QC is greater than KC, then at that time, the concentration of product is higher and the concentration of reactant is very lower than KC value. That's why the reaction will shift in the reverse direction. Okay. So this is the case and the relation between how you will identify which direction the reaction is going to take place. But tell me how this is possible, like when QC is greater than KC. This is possible if you add a product from outside or if you remove the reactant from the reaction, then the QC value can be greater than KC value and then reaction will shift in accordingly to nullify the effect. Clear? Now, for example, why I'm talking about QC and KC, for example, you are given with this reaction. One second. A plus B forms 2C plus D. Okay. Gas, 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 and gas. Now, you are given that initially, when the reaction did not even start, the initial moles were 2, 2, 2 of each of them. Right? Now, the Kc value of the reaction is 1. Okay. How you will know the reaction is going to go in a forward direction or in a reverse direction? Because already the components, there are certain moles of reactant and certain moles of products before the reaction even start is present, right? So it can go in a forward direction, it can go in a reverse direction also. So what we can do is we can find out the value of QC at this point. So the value of QC is 2 raised to power, so value of QC is concentration of C raised to power 2, concentration of D, and concentration of A into concentration of B, right? So C is 2 the square into 2 upon 2 into 2. So the value is 2. Now the QC value is 2. It means QC value is greater than KC value. It means the concentration of product is already high than the equilibrium concentration. Therefore, reaction will shift in a backward direction. Okay, so when you are going to make the ICE table for such reactions, it will be like A plus B forming 2C plus D, 2, 2, 2, 2. Now the change will be minus here because the reaction is going to move in a reverse direction. So the concentration of C and D is going to reduce and the concentration of A and B is going to increase. Okay, so this will be 2 plus X, 2 plus X, this will be 2 minus 2X, and this will be 2 minus X. Okay, so this is why we need to have the value of QC so that we can compare if the reaction is at equilibrium or not at equilibrium, and if it is not at equilibrium, which reaction it is going to go ahead. Clear? Any doubt? Next is how the equilibrium constants are going to change if we bring some changes into the reaction or if we multiply the reaction with something else. So for example, you have this reaction A plus B is going to form C plus DD. All are in the gaseous state. Okay. Now the value of Kc is K1. And then you are being asked for the reaction, the Kc of the reaction, this. Okay. So this is Kc of this reaction, which is equal to K2. So what will be the relation between K1 and K2? See, the reaction is same. Nothing has changed. It's just it has been reversed. So when reaction is reversed, then the equilibrium constant is 1 by the equilibrium constant. Means Kc is equal to the first reaction. If Kc is equal to K1, for the second reaction, it will be 1 by K1. So if the reaction is reversed, the equilibrium constant will become 1 by of that initial equilibrium constant. That's why K1 is equal to 1 by K2. Okay. Second point is, if we multiply the equilibrium constant, the equation with some number, means, for example, you are given with reaction SO3 is going to form SO2 plus half O2. And if the equilibrium constant is K1. Then what is the equilibrium constant of 4SO3 to 4SO2 plus 2O2? So what we have done, we have just multiplied this whole equation with 4, right? So the Kc value of this reaction is K1 raised to power 4. Okay, it will increase in terms of power. We can see also because these stoichiometric coefficients are going to go in the terms of power. For example, if I'm going to express Kc of the first one, K1, it will be SO2 concentration of O2 raised to power half and concentration of SO3, right? Whereas if I write down the K2, this equation, the Kc value, it will be SO2 raised to power 4, O2 raised to power 2, and SO3 raised to power 4. So what is it? It is the 4 times of K1, right? That's why it will go in the power, okay? And then third, if you add two reactions, means you have A plus B forming C and D plus E is forming F, okay? And this is K1 and this is K2, and you have to find out the equilibrium constant for A plus B plus D plus E forming C plus F. So this net reaction is what? This net reaction is nothing. It's just the addition of the above reactions. So in such cases, the net equilibrium constant will be the multiplication of K1 and K2. So the K equilibrium for this reaction will be equal to K1 into K2. Okay. So this is how it can be solved. Fine. So this is about how the equilibrium constant are going to change. Let's take an example. So the equilibrium constant of the reaction SO2 plus half O2 is SO3. Fine. The Kc value is 4. Fine. Now you have to find out the Kc value of 2SO3 is going to form 2SO2 plus O2. Okay, we have to find out the Kc value of this reaction. Now, how we are going to do that? Nothing. See, first, what operation has been applied here? The reversal of the equation. So we have reversed the equation. So Kc dash will be reverse of this, right? But we have also multiplied the equation with the factor of 2, so raised to power 2. So it will be the Kc dash, means Kc of this will be 1 by 4 raised to power 2, which will be 1 by 16. Okay, so this is how we are going to solve the equations, like the questions where the Kc value has changed, and yeah, and how we are going to work on it. Clear? Now, this is all about the KCs, KP, and K-equilibrium, like how we can define them, what is the relationship between them, and these type of questions come very frequently in your exams as well. So I hope these concepts are clear to you, and we will be going ahead in the next class where we are going to talk about the degree of dissociation, we are going to talk about the Lee-Chatterless principle and all that stuff. And also we are going to do some questions about whatever we are calculating here. So stay tuned. If you have any doubt, please post your doubts in the chat window, in the comment section basically, and do let me know if you want me to explain some specific topic. I hope you all have understood this, and please subscribe and share with your friends. Okay. Thank you so much, guys. Tata, bye-bye.